Okay. Hello, everybody. So this is an out-of-sequence class. So I mentioned Feynman diagrams several times, and I mentioned that what we do is related to Feynman diagrams, and which come from physics originally. And I felt it was wrong not to make the connection a bit closer. Okay? So I'll tell you a little bit about Feynman diagrams, but obviously, okay, so a part of it will be fully rigorous in a sense, or fully complete, and a part of it just no way cannot be complete, okay? So the part that cannot be complete is the motivation from physics. So physics has something called QED, and it's not the same as what mathematicians call QED, so it's quantum electrodynamics. And it's the most successful quantum field theory there is. It's the one that actually does computable predictions, not just qualitative predictions, but you actually compute numbers and they come out, you know, through to 6 digits after the decimal. It's really a good theory. Here is all of quantum electrodynamics in a small box, made very, 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 very schematic. So the point is, or you know, you must have heard of path integrals. So path integrals, you know, somehow say that particles in quantum mechanics go from one point to another along all passable paths, and then for each path you compute some quantity and you sum over all, you compute some amplitude, you sum over all paths, and then that's the overall amplitude to go from point A to point B. And you know, what I said is completely informal, but you must have heard it as an informal thing. It's part of the stories that everybody tells. The same is true for electromagnetism. So electromagnetism is defined by having, or is a field theory. So instead of a particle going from one place to another, you have fields. Fields are essentially functions on R4. And if you want to see how a field evolves from one point in time to another point in time, you integrate over all possible ways of evolving a certain amplitude. Okay? So it becomes an integral over a space of functions, because the fields themselves are functions. And also they depend on time. So all of quantum electrodynamics is summarized by there is a pair of functions, basically the electromagnetic field A and the electron field psi, and you integrate over the space of all functions. So this calligraphic D means not well-defined integral. Unlike lowercase d, which stands for honest Lebesgue integration or Riemann integration, this is an integration over an infinite dimensional space, the space of all functions, and strictly speaking, it doesn't exist. At least for mathematicians, it doesn't exist. Yet physicists write formulas like the integral dA, so the integral over all electromagnetic fields, the integral over all electron fields of the exponential of I times the Lagrangian, where the Lagrangian itself, very, very, very schematically, is an integral over R4 of, sorry, that's the action. The Lagrangian is the thing under the integral sign. Anyway, well, let me still confuse the name. So the Lagrangian is the integral over R4 of the derivative of A squared plus psi psi times the derivative of psi minus psi squared plus 1 over 137 times a psi squared. Okay? Now, this is absolutely schematic. So a is not really a single function. It's a quadruple of functions, or more precisely, it's a one form. Psi is also not a single function, but it's a section of some bundle or something, but in fact it's also so-called fermionic, whatever that means, okay? And so this derivative is not really a single, it's a schematic for a derivative. I really mean the differential in the sense of differential forms, and then this is a two form, and the square really is the norm of that two form. Likewise, it's only schematic. In fact, these two terms together, well, this is just the norm, but these two terms taken together are the covariant derivative of psi relative, well, you know, the actual meaning is harder, but schematically that's what you see. The only thing that's actually accurate in this equation are the degrees of the variables and the 137. The 137 is the fine structure constant, and it's actual. This is the actual value, and it's a small number. So if you look at this expression, it's quadratic. This is quadratic in A, this is quadratic in psi, this is quadratic in psi, plus a cubic perturbation. And the perturbation really is a perturbation because it comes with a small coefficient, so it's small. And in fact, the whole success of quantum electrodynamics is because of some lucky coincidence in nature in which this number is small. Okay, similarly, there is another very successful, well, theory inspired by physics. It's hard to say that it's physics because it's really theory with a lot of mathematical consequences. It's the Chern-Simons-Witten theory. And again, it's an integral over, it's a path integral, an integral over an infinite dimensional of space of fields of the exponential of something which is quadratic in the field plus something cubic. And even though 2/3 doesn't look like a small number, there are actually more coefficients that I didn't indicate, and in some sense, the cubic part is small, can be regarded as small. So in general, we want to understand, integrals that have a potentially large the exponential of some of a potentially large quadratic part plus a perturbation which could be cubic but could be higher than cubic, but you know, in the two examples that I gave, the perturbation is cubic. So what's going to happen is these are infinite dimensional integrals. We have no clue how to compute them. So what we're going to do instead is understand the finite dimensional analogues or finite dimensional analogues of these integrals, and then in finite dimensions, we will evaluate these integrals using, so basically, we will replace these integrals by integrals over Rn, and then we will actually completely evaluate them. And the evaluations will end up depending only on summations, where the summation variable runs from 1 to n. And here, these are functions. So functions really are really R to the R. Okay, very, very loosely. So we will copy the formulas from here, or not we will, the physicists copy the formulas from here, and then summation from 1 to n, summation over n things, become summation over r things, but that's just ordinary integration. So, once we understand how to do finite dimensional perturbed Gaussian integrals, well, if we were physicists, we would use it to compute these integrals we really, really want. And the understanding of how to do finite dimensional perturbed Gaussian integrals turns out to be very similar to the kind of things that we've done. In fact, we will have a formula saying that if you want to compose two generating functions, the composition formula I wrote so far, well, I had several formulas, but one formula was you multiply the two generating functions and you apply the exponential of some sort of a Laplacian, so some d to dz, d to d zeta. Okay, that was the composition law we had so far. And I will tell you that up to some normalization constant, this can be rewritten as an integral. So instead of basically, instead of this infinite dimensional, instead of this infinite order differential operator, you have, the L times m stays, but then instead you have a Gaussian integral. And this means that if you fully understand, if you understand Gaussian integration very well, you actually can deduce or you can learn about the compositions that we care about. And hence the analogy. Okay? So why didn't I do this from the start? The answer is, well, this is actually way more complicated. Integration is not an algebraic operation. Differentiation is. So this is a way more complicated thing, and in fact, these integrals are not really convergent. If you really want to make sense of it, you have to work a lot harder than what we did. Okay? Still, it's worth going through it because of the relationship with Feynman diagrams and because of the fact that many more people, for historical reasons, have intuition about how to integrate than how to apply infinite order differential operators, even though this is intrinsically easier. Okay, so we want to understand a finite dimensional analog of, say, quantum electrodynamics. And here it is. So we want to understand integration over Rn of some dx, where x is in Rn, and the integrand should be the exponential of minus 1/2 lambda ij xi xj plus epsilon over 6 lambda ij k xi xj xk. And let me explain what is written here. So x is really a variable in R to the n, so it has components x1 up to xn, and I put the indices on top. This part is the quadratic part, and or the quadratic part of the exponential. So this is a general quadratic form, namely it's xi xj multiplied by a coefficient lambda ij. So and then this is summed over I and j, but I use the physics convention that if you have repeating variables, it automatically means that they are summed over. So I don't need to write the summation. So there is implicitly a sigma here, but I just didn't bother to write it. So lambda ij is the matrix of coefficients. So lambda ij, which I will also call uppercase lambda, is a, well, since it's a quadratic form, it may as well be a symmetric matrix. Symmetric matrix, so it's a symmetric matrix. And also, you see now we are in R to the n, so we can pretend that these integrals are meaningful. And then you would probably want this matrix to be positive definite, so that you will be exponentiating something that grows rapidly minus something that grows rapidly. So therefore, the integrand will be shrinking rapidly. So maybe you want to say positive definite matrix, but it actually doesn't matter a lot. Notice that this matrix is not positive definite. The quadratic form that appears here is not positive definite. And finally, okay, the 1/2 is there just to make formulas simpler. Likewise, the 1/6 here is just to make formulas simpler. And the epsilon is the small coefficient. So in quantum electrodynamics, this would be roughly 1/137. Sorry, 1/137, yes. Lambda I, J, K are coefficients of the cubic term. The general cubic term is x to the I, x to the j, x to the k. So I want to know how to compute such integrals as a function of epsilon on the assumption that epsilon is tiny. Okay? Is this familiar, by the way? To some of you it should be, because I don't know. Anyway. Okay, let's start. So basically I'll do it in order. So calculation number 1 is, let's just do the Gaussian thing, assuming lambda is a single constant instead of a matrix, and drop the cubic thing. Cubic thing will come later. So case number 1, let's do the integral of e to the minus lambda, the absolute value of x squared over 2 dx. But let me do something funny. I actually want to do it on r squared, not on r. On r squared it is easier than on r. Why is it easier on r squared? So on r squared, you can switch to polar coordinates, right? So every point has an r and a theta, and you can switch to polar coordinates. And this becomes the integral. So theta runs from 0 to 2 pi, I believe. R runs from 0 to infinity. There is a Jacobian, if you remember the polar coordinate. The Jacobian is r. And then x squared, the norm of x squared is simply r squared. So this is e to the minus lambda over 2 r squared. Okay? And by luck, this function has a primitive, right? A definite integral. So this becomes, okay, sorry, let's do it in order. First of all, the integral d theta, all of this is independent of the theta. So from the perspective of theta, it's a constant, so the integral d theta just gives 2 pi. So this is 2 pi times, and then this function has a primitive, so this is the primitive of this function. What is it? E to the, no, it's minus 1 over lambda e to the minus lambda over 2 r squared, evaluated from 0 to r. Right? Because if you differentiate this with respect to r, then the exponential stays, the internal derivative of this has a minus r times lambda, sorry, is minus lambda r, and minus lambda r, well, the minus and the lambda cancel, and you're left with the r that's here. Okay, so this can be computed explicitly, and okay, now you sorry, it's not from 0 to r, it's from 0 to infinity. Now, at infinity this vanishes. At 0, you get e to the 0, which is 1, so you get 1 over lambda, with a minus sign, but it's the lower limit of integration, so the minus cancels. So you just get 1 over lambda, but then the 2 pi stays, so you get 2 pi over lambda. Okay. Claim, it's funny, but it's easier to go from 2 dimensions down to 1. So claim, now if you do the same in just 1 dimension, so you compute e to the minus lambda x squared over 2, the integral dx, but it's over r to the 1, claim is that you get the square root of this. The square root of 2 pi over lambda. Proof, well, take this thing and square it. So, I don't know, call this quantity I, and let me compute I squared. I squared can be written as, oh, you know what, maybe I should have done it differently. No, let me do it differently. Let me start with this integral, but write it differently. So this is the integral. Now let me separate the roles of x and y. So it's the integral dx dy over r squared of e to the minus lambda x squared plus y squared over 2. But this is the integral over r squared of e to the minus lambda x squared over 2, e to the minus lambda y squared over 2, dx dy. By Fubini's theorem, right, these factors, this is a function that depends only on x, this is a function that depends only on y. So by Fubini's theorem, this is the integral over r of e to the minus lambda x squared over 2 times the integral over r e to the minus lambda y squared over 2 dy. But this is the same as that, and both of them are equal to the integral I wanted. So this is I squared. But so I squared is 2 pi over lambda, so I is the square root of 2 pi over lambda, QED. Okay. Claim 4. No, I can't count. This was calculation 1, so this is claim 2. So now let's do claim 3. Claim 3. So now if lambda ij, which is equal to lambda, is symmetric and positive definite, so that the integral at all makes sense, then the integral over all of x's, so x runs in r to the n, of e to the minus 1/2 lambda ij xi xj is equal to 2 pi to the power n over 2 divided by the determinant of this matrix, lambda ij. So by the determinant of the matrix uppercase lambda. Proof. So clearly it's true for diagonal matrices, true if lambda is diagonal. If lambda is diagonal, then this is just a sum of, right, so if lambda is equal to, if lambda is equal to lambda 1 up to lambda n, then the quantity here, so this thing becomes minus 1/2 sum lambda I xi squared. And then, again using Fubini, the integral splits. Like for each xi, it's a separate integral. And each of them gives the thing written here. The thing written here is 2 pi to the power n over, so it's 2 pi to the power 1/2, but n times, so you get 2 pi to the n over 2, times, oops, square root of the determinant of lambda, I got it wrong, times, well, in each dimension, you'll get the corresponding lambda, so you'll get the product of the lambda i's, and the product of the lambda I, sorry, to the power 1/2, but the product of the lambda i's is the determinant of the matrix. So what I wrote is correct, and what I wrote previously was not correct. Anyway, but now if lambda is not diagonal, then it can be diagonalized by an orthogonal matrix. That's a fact from linear algebra. So it can be diagonalized by an orthogonal matrix, and an orthogonal matrix is measure preserving. I mean, if you rotate r to the n, you don't change the measure. So the integral doesn't change. And so you still get the determinant here. Okay. So this is essentially it. Okay. And now here's a disappointing fact. So let's call this quantity C. And from this point on, it's completely irrelevant what is the value of C. The only reason I've computed it is so that it will not look like a miracle. It's just a number. It has a formula. I actually don't care what the formula is. I just didn't want it to look like a miracle. So I computed it. But now you can forget where it came from. Sorry, not where it came from. You can forget what its value is. Who cares? I don't care about this. Okay, but now let's do something that I do care about. So, claim number 4. So now I want to integrate over r to the n, instead of simply a Gaussian, a polynomial times a Gaussian. So let's compute the integral of p of x times e to the minus 1/2 x transpose lambda x. This is the same as that, except I wrote it, here I wrote it as a summation with dropping the summation symbol, and here I use matrix multiplication. It's the same thing. And I forgot the dx, so I should get a point removed. So the claim is, okay, sorry, I should have said, this is a polynomial. So, and it's a polynomial in all of the coordinates of the xi's. Okay, so it's not, okay, it's a polynomial in many variables, in n variables, in principle. So the claim is that this is the following. So you introduce dual variables to the variables x. Okay? The funny thing is that these aren't the dual variables that we've been using all the time. They're dual in a different sense. They play a different role. So I don't want to call them xi's, because the xi's play this role, and in fact, the z's and the zetas. So basically, I'm introducing dual variables to all integration variables. Here the integration variables are both the z's and the zeta. So really, I should be using, Z star and zeta star, okay? Which are, it's a different duality. So I need sort of a new notion of a dual variable. So since, had there been, maybe I should have used some letter from a Ghanaian alphabet or a Hebrew alphabet, but since we don't all know these letters, let's just call them Y sub I. And I've switched the indices to be down indices because down indices are sort of due to up indices. Okay, so the claim is that what you get here is you take the polynomial, and every place you see an xi, you replace it by differentiation with respect to yi. So d to dy. This is a finite order differential operator. You apply it to e to the 1/2 y transpose lambda inverse y, and evaluate all of this at y is equal to 0. Okay? So let me emphasize, or the point, what's the point? The point is that this is an integral, oh sorry, and I forgot the constant c. Multiplied by that same constant c of before, which we no longer care about. So what's the point? The point is that this was an integral, maybe a hard integral. It got replaced by a finite amount of algebra. This you can differentiate using the chain rule and the Leibniz's rule, whatever, in a finite amount of time, because p is simply a polynomial. So you replace integration by a finite amount of algebra, and this in algebra only involves summation 1 through n, 1 to n, because, well, that's the only thing that appears here. So summations running from 1 to n. So we have achieved, so if this is true, we're close to achieving the goal. Okay? And therefore, if we will translate it to infinite dimensions will reduce to something that potentially is computable. Okay. And one more comment. Basically, from this point on, we completely forget about convergence. In a way, we turn this into a definition. So if you want to integrate this, the answer is that, and you even drop the constant, who cares? But that will come later. So anyway, let's prove this claim. So the first thing to do is clever. So you replace this by P. By the way, have you seen these things before? Okay, so you replace it by P of d to dy applied to the integral on r to the n, e to the minus 1/2 x transpose lambda x plus the pairing of y and x, so y dot x, or y transpose, basically the inner product of y, the duality between the y's and x's. Dx. Okay, the point is, when you, and evaluate at y is equal to 0. The point is, when you, every time you differentiate with respect to a yi, this term doesn't see it, and this term has a yi times an xi. So every d to dy pulls down an xi to down here. So applying some polynomial in d to dy to this will pull down the corresponding polynomial in the x's. And then you substitute y is equal to 0. So this, at the end, you substitute y is equal to 0, so this drops. So you got exactly that. Okay? But now we need to compute this. To compute this, we first do something clever. We so-called complete the square. So Q is a quadratic, so I can rewrite it in the following way. I can rewrite it as -1/2 x minus lambda inverse y transpose lambda x minus lambda inverse y. This is nearly correct. The point is that if you have a quadratic plus a linear term added, by the way, this has analogs in R squared. So basically, if you have a quadratic plus a linear term added, it's just a quadratic about a shifted point. Instead of a quadratic around 0, it's a quadratic around a shifted point. So that's what I'm doing in general. I have a quadratic plus a linear term, and I rewrite it as a quadratic where you shift the variable. So instead of x, instead of x and x transpose, you get x minus lambda inverse y and x minus lambda inverse y transpose. Sorry, this is philosophy, but now if you just open parentheses, you find that it's true, nearly true. So basically, the x, if you take the x from here and the x from here, you get the term you wanted. If you take the x from here and the lambda inverse y, you get this term. Actually, you get x transpose times y, but it's the same. But you get it with a factor 1/2. But you need to get it with a factor 1. But you also get that term by looking at the lambda inverse y from here and the x from here. Because lambda is symmetric, so lambda inverse y transpose is y times lambda inverse, and the lambda inverse cancels this lambda, and you're just left with, and then it gets multiplied by x. So 3 of the terms here give you the 2 terms here. But there is an extra term here. In fact, this has to do with the fact that the quadratic is not has its minima not equal, not on the x-axis. So anyway, there is an extra term here, namely the lambda inverse y. So we have to subtract it off to make it correct. So let's subtract it. So we need to subtract 1/2 y transpose lambda inverse y, but I think I miscounted the signs. So the term we get has 1 minus, second minus, third minus, so 3 minuses. So it comes with a negative term, so I have to add it back again. And now it's a correct equation. Okay? So this integral is equal to p applied to d to dyi applied to the integral over r to the n of, let's call this q1 and let's call this q2. So here I have e to the q1 plus q2 all at y equals to 0. Okay? But now q2, sorry, this is an integral dx. q2 is independent of x. So I can pull it out of the integral. So I have that this is p of d to dy I, and then I pull e to the q2 out of the integral, so I get e to the 1/2 y transpose lambda y times the integral of e to the q1 dx. All of this at y is equal to 0. But q1 is just a shift, a translation of the formula written here. This is the formula written here, not here, here, in which you make the substitution x goes to x minus lambda inverse y. Lambda inverse y is a constant from the perspective of this integral. So it's translation by a constant amount. So by Lebesgue invariance, this integral is exactly the integrals that we've already computed. So this is c. So the conclusion is that we get c times p times, well, the conclusion is that we get what I promised. Okay? End of story. By the way, at this point, we can justify this composition formula. So you see, sorry, I removed, well, I should have erased this. But anyway, so you see, this is, okay, sorry. So, I mean, in the composition formula, L and M were power series. I'll, just so that I don't have to worry about convergences, let me justify the composition formula for polynomials. So if L and M are polynomials, this is again a polynomial. So really this is a Gaussian integral. So this is the integral of the exponential of a quadratic times a polynomial. So it doesn't make sense because this quadratic form is actually not positive definite. But I'll apply the same. I'll do exactly the tricks that the physicists do. Namely, I'll apply the formulas as if they made sense. Okay? And you could justify it. You could spend a lot of energy justifying it. Namely, instead of using real numbers, you could have inserted an I here. And then it would be an imaginary quadratic form. And then this would be a complex number of modulus 1. And then, well, it's still not L1, but at least it's well, it's kind of as defined as the Fourier transform, or it's close in nature to the Fourier transform, and you can do similar things and make it properly defined. But, well, this is so let me just say that the fact that this is proportional to that is loaded. And I don't want to unload it because this formula is simply correct with no issues and no problems. So I'm really showing the similarity with integration only for cultural reasons. It's not really for being useful. Anyway, having said all of this, this becomes, using the formula over there, it becomes L times M evaluated on differentiations with respect to the dual variables. So D to, so L and M depends on Z and Zeta. So let's call it D to D Y, D to D Y B, D to D eta B. where y is the dual of z and eta is the dual of zeta. Okay? All of this computed at, or so this differential operator acting on, so you had to invert the quadratic form, but also invert the sign. So, so the quadratic form is the inverse of the quadratic form here, but with a plus sign. Now, what is the quadratic form here? The quadratic form here is the quadratic form represented by the matrix 0, I, 0. It's a quadratic form in 2n variables, and it's represented by this matrix. So the inverse of this matrix is itself. It's again 0, I, 0. So here you will get the same quadratic forms, but with the letters replaced by their duals. So sigma yb eta b, and all of this evaluated at y equals eta equals to 0. Okay? But you see, differentiating, and this is a sort of a symmetric expression in the variables and their duals. This just counts the number of, well, we've seen this already. So, this is, I mean, this is the same as putting as thinking of these as the differential operators. And so, okay, so basically differentiating and evaluating at 0 is just counting the number of times things appear in equal degrees here and here. But you can count it the other way around. Namely, you can put the differential operators here and differentiate that, provided at the end you evaluate at 0. And that's exactly what's written here. Okay? So, so this proves up to loaded scalars, up to loaded proportionality factors, this proves the identity we wanted. Okay. Well, we have 1 minute to go, so I'll, that's enough time just to state what I want to say, but not say it. So next is, so remember that I really wanted to compute the integral of e to the minus 1/2 lambda ij xi xj plus epsilon over 6 lambda ijk xi xj xk. Okay? So, this is not a polynomial, but I can write it, but I can expand it as a power series in epsilon, and then if I want to just compute it, if I just want to compute the expansion in epsilon, it becomes a sequence of polynomials. So basically, this is equal to the sum as n goes from 0 to infinity of the integral dx of epsilon to the n divided by n factorial, and in fact I can also put the 6 to the n out, and then lambda ijk xi xj xk to the power n e to the minus 1/2 lambda ij xi xj. Right. I just expanded in epsilon. But now, each of the terms of the expansion is just a polynomial times a quadratic, times a Gaussian, which we already know how to do. So therefore, this is equal to that same ugly constant times some pairing of some differential operator with some quadratic. And it's this that we have to understand next time. Okay, let's stop.